After the completion of kinematics of rigid body, we should start thinking of the dynamics of rigid body. But in dynamics, we use two terms, torque and angular momentum. Just like the force is the cause of linear motion of an object or of a particle, similarly, the torque is the cause of angular motion of a rigid body. Force changes something. That something is called linear momentum. When you apply a force on a particle, the linear momentum of the particle or the group of or system of particles will change. At what rate the momentum of the group of particle or a single particle is changing, that's equal to the force acting on that system or a particle from outside, or the external force. The external force is equal to rate of change of linear momentum. So the force changes something which is known as linear momentum. Similarly, in rotational mechanics, the torque is the cause of rotation and it changes something. That something is called angular momentum. And in this chapter, we will study the relation between the force and the torque and the angular momentum. First of all, we should deal the idea of torque. Torque of a force measured with respect to a given point. Torque of a force about or with respect to a point. This point may be moving, this point may be fixed. For the sake of simplicity, let us assume that this point moves with a constant velocity or the point is stationary. When a point moves with a constant velocity or a stationary point, we can call it inertial reference point or inertial reference frame. What is the meaning of the torque? Torque is the rotational effect of a force. If I write, it is the rotational effect of a force. What is the meaning of rotational effect? For instance, you take this pen. This is hanging. When you apply a force, what happens? This is rotating. When you apply a force, it is rotating. When you apply the force in this way, when you pull it down, it's not changing its angle of orientation. This means that it's not rotating when you apply the force down. When you pull it down or push it up, is it rotating? You can say that it's not rotating. Therefore, force, when you apply a force, it may not be the cause of rotation. Therefore, force cannot be attributed to the cause of rotation. Hence, there must be some other quantity other than the force which should be or which must be responsible for rotation of an object. Well, experiment on the same piece of pen. When you apply the force here, it is easier to rotate. When you apply the force here, it is more difficult to rotate. When you apply the force here, you cannot rotate this object. When you want to rotate it quickly, you have to apply more force. Less force, less rotation, more force, more rotation. Well, so how much force you are applying? At which point you are applying the force, in what direction you are applying the force. All these three quantities will decide whether this body will rotate or not. How fast this body rotates, that is decided by the three quantities, the three things. Number one is how much force you are applying. Number two is which direction you are applying the force. Number three is where exactly you are applying the force. It is understandable that when you are applying the force further from the pivot or the axis, this is the axis of the pivot. When you apply the force further from the pivot, more easily you can rotate it. When you apply the force nearer to the pivot, it is more difficult to rotate it. So the ease of rotation, of this object, suppose it is hanging here. When you apply the force here, 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 apply the force here. There are 7 positions. Suppose you apply the force perpendicularly. Practically it is evident that it is most easily, or it is easiest to rotate when you apply the force at this point, and it is impossible to rotate the object when you apply the force here. So where we are applying the force, this is important. And we can understand that when you are applying the force further from the axis of rotation, when you apply the force at the further points, you can rotate the object more and more easily. So the furthest point at the end of the rod, when you apply this force, most easily you can rotate it. So the ease of rotation depends on the point of application of the force, where we are applying the force, that is important. And if you want to rotate the body more quickly, you can apply the force at some given point. Suppose point 3 is the given point and you are applying the force here. When you apply the force F, you can rotate it. When you apply the force to F, more quickly you can rotate it. It can produce more angular acceleration. When you apply the force 3F on the same point, in the same direction, for the sake of simplicity, you are pushing that point perpendicularly, up normal to the rod. When you increase this magnitude or amount of the force, more quickly this body will rotate. More quickly means angular acceleration is more. So the ease of rotation also depends on how much force you are applying. If you apply less force, less quickly the body will rotate. If you apply more force, more quickly the body will rotate. Well, the third factor, the same rod, if you apply the force in this way, you apply the force in this way, you apply the force in this way, if you apply the force in this way. Suppose this is the force, the forces F1, F2, F3 and F4, and their magnitudes are equal, say, for the sake of simplicity of analysis, and directions are different. Another, suppose F4. Four forces are equal in magnitude. Can you tell me in which direction you have to apply the force such that or so that the body will rotate in easiest manner? It's quite clear. When you push the object, apply the force up, it won't rotate. When you apply the force down, no chance of rotation. Therefore, F1 and F2, F4, F1 and F4, no chance of rotation. Alpha will be 0. But if you go on increasing the angle from both the sides, you can take some more inclinations, more angles. From this side or from this side. From both the sides, if you go on increasing the angle, you can see that most easily the rod can be rotated when you apply the force perpendicular to the rod. So, the third thing is in which direction you are applying the force. So one thing is very clear, to rotate the object, how fast you are rotating the object, how easily you are rotating the object, how easily you are twisting the object, that depends on these three quantities, three factors. The twisting effect of the force is known as torque. The twisting effect of the force is known as torque. Torque is a Greek word. Torque means twist. The twisting effect of the force is called torque. Force has two effects. One, it can speed up or slow down an object or center of mass of the object. The another effect is you apply a force, it rotates or it is getting twisted. The twisting effect of the force is called torque. How easily the body is rotating or is twisting depends upon three factors. Factor number one, the point of application of the force, where we are applying the force. If you are applying the force nearer to the axis, more difficult for us to rotate the object. When you are applying the force further from the axis, with less difficulty or more easily, we can rotate the object. So the ease of rotation depends upon where you are applying the force and how much force you are applying. If you apply more force, more quickly the body will rotate. If you apply less force, less quickly you can rotate the object. The third thing, in which direction? It's not just to pull that point or push that point. In which direction you are pulling? Suppose I am pushing in this way and I am pushing in this way, or I am pulling in this way, I am pulling in this way, I am pulling down, I am pulling up. When you pull down or up, it won't rotate. When you pull at some other direction, it will rotate. But when you pull perpendicular to the rod, it will rotate maximum. The ease of rotation is maximum. The twisting effect is maximum. Therefore, in which direction you are rotating, in which direction you are applying the force, this also decides the ease of rotation. So, symbolically you can write where you are applying the force, that is the distance r. that is given by the distance of the point of application of force. This is the point of application of force, and this is the axis of rotation. From axis of rotation with respect to a point, this is the point O. With respect to this point, we are measuring the twisting effect or the turning effect. This can also be called twisting or turning effect. Turning effect of the force is governed by, is controlled by, or is governed by three factors. Here we are applying the force, means the distance of the point of application of the force P from the given point or reference point O. This reference point is pivot. From the reference point, here you are applying the force that is decided by, is given by, or symbolically is given by R. Well, so it depends upon R. If R is more, the torque is denoted by the symbol tau. Practically, it is evident that when you go on bringing the point down and down and down, or further from the axis, or further from the reference point, the turning effect is more, is directly proportional to R. Practically it is proved that the turning effect is more, means the angular acceleration, turning effect is given by angular acceleration. The turning effect is more when R is more. Well, how much force you are applying? The turning effect or angular acceleration is more when the magnitude of the force is more. When you push it or pull the point with more force, keeping the angle theta constant. The turning effect is directly proportional to the magnitude of the force. Also, it is proportional to the third quantity. What is the third quantity? Direction. In which direction you are applying the force? When theta is 0, suppose you take theta, this angle theta. Theta is the angle between the R vector and F vector. If you take other angle will be theta. For instance, this is the force. This is R vector. Force vector and R vector. R is the position vector of the point of application of the force with respect to the reference point O. Position vector of the point of application. What is that point? Point P. At this point you are applying the force, and this is the reference point. So R vector and F vector. Bring these two vectors to a point, bring the tails of these two vectors to a point, the angle between these two vectors is theta. So what is theta? Theta is the angle between these two vectors. So in which direction you are applying the force? Direction is given by theta. How much force you are applying? This is the magnitude of the force. And this is the magnitude of theta, I will tell you. Practically, it is evident that the turning effect or the twisting effect or the torque, which is quantified by, measured by the kinematical term angular acceleration, is directly proportional to the distance of the point of application of the force with respect to the reference point, also directly proportional to the magnitude of the force, the amount of the force you are applying. Now the third quantity, let us discuss. Based upon this experiment, you can understand that the body will not rotate when the angle theta between R and F, the angle theta. The angle between R, this is R vector, this is F vector. This is theta, this is theta, this is not theta. However, sin theta can be approximated to sin 180 minus theta. That is different thing. But theta is the angle between R vector and F vector, where theta is the angle between R vector and F vector. What is R vector? The position vector of the point. Which point? At which you are applying the force, for which you are calculating the turning effect or the torque or the moment of application of that force with respect to the reference point O. Position vector of this point P with respect to the reference point O, that is R. And the turning effect is directly proportional to R, directly proportional to the amount of force. And third thing is given by sin theta. Why sin theta? Why not cos theta? Why not tan theta? Because when you apply the force down, when you pull this point down, there is no chance of rotation. When you pull it, is it rotating? No. When you push it, is it rotating? No. When you pull it, for pulling, theta is equal to how much? 0. For pushing it up, pulling down. For pushing up, theta is equal to 180 degree. When you are pulling, this is R vector, this is F vector. Theta is how much? 0. For pushing, this is R vector down and F vector up. So this theta is how much? 180 degree. For when theta is 0, no turning effect. When theta is 180, no turning effect. Which function will give this? And turning effect is maximum when you push it or push that point perpendicular to the rod. Maximum is with most efficiently, in easiest way, you can rotate the object when you adjust the angle between the force and the R vector as 90 degree. So when theta is 90 degree, most easily we can rotate or produce maximum angular acceleration. Therefore, the only function which can satisfy this 0 at 0 degree, effect is 0, no turning effect, 0 turning effect at 0 degree, 0 turning effect as 180 degree, 0 turning effect at 180 degree and maximum turning effect as 90 degree. Which function will satisfy? The sine function will satisfy. Therefore, you have to put sine theta, no cos theta, no tan theta. So the torque is directly proportional to the R, is directly proportional to the F magnitude, is directly proportional to the sine theta, where theta is the angle between R vector and F vector. As a whole, if you combine these three effects, all these three effects as a whole will decide whether the body should rotate or not. The combined effect of all these three is called the turning effect or torque of the force. You take any rigid object, pivot it. Let us assume that this is a reference point O. This is the point which has the position vector R at which you are applying the force F. This is the position vector, and the angle between the position vector and the applied force is theta. This is the position vector, this is the applied force. This angle is theta, it's wrong. For the correct theta, the correct theta is the angle between the force and position vector. You bring the tails of these two vectors to a point, and the angle between these two is the angle theta. Well, when you apply the force in this way, rotating inhibitions, anti-clockwise sense, how we can see that? When you apply the force in opposite sense, say in this sense, this is R, this is F, this is R, this is F. The angle between these two vectors is theta. This is not theta, this is theta. This is theta. This is correct, this is wrong. Bring the tails of these two vectors, tail of the force vector, tail of the R vector. Bring the tails of these two vectors to a point. The angle between these two vectors is the theta. Well, this is the pivot, this is the point where you are applying the force. Where you are applying the force and for which you are calculating the turning effect or torque about this point. Let tau be the torque or twist or turning effect or moment of force about or with respect to or relative to point O. This is a reference point. Practically, it is evident that this turning effect of the force is directly proportional to the distance, directly proportional to the magnitude of the force, and also directly proportional to the sine of the angle between these two vectors, R vector and F vector. Taking all these three effects, effect 1, effect 2 and effect 3 into account, torque is directly proportional to RF sin theta. Many times in physics, when you equate both the sides, we take a constant of proportionality, and here the constant of proportionality, let it be K into RF sin theta. When you multiply, then you are getting the torque. For the sake of simplicity, we put K is equal to 1. to get torque is equal to Rf sin theta. R is a vector quantity, F is a vector quantity. Vector A into vector B, magnitude of vector A into the magnitude of vector B into the sine of the angle between these two vectors can be written as A cross B. Here vector A is R, here vector B is F. Rf sin theta can be written as the cross product of two vectors R and F. Then you can write vectorially torque is given as the vector product of R and F. Since the product of two vectors, the cross or vector product of two vectors or cross product of two vectors is a vector quantity, this torque is a vector quantity. Because the turning effect has a clockwise sense of rotation. You push it like this, you rotate in which sense? The anti-clockwise. When you push it like this, you rotate in which sense? Clockwise. When you apply the force in this way, this is the direction of torque. When you apply the force in this way, this is the direction of torque. When you apply the force in this way, this is the direction of torque because it will rotate in this way from rest. It was at rest. When you apply the force, it will rotate in this way. It was at rest. When you apply the force, it rotates in this way. Rotation means what? At rest means omega initially 0. When it rotates, its omega changes from 0 to non-zero. This means that angular acceleration. Rotation means here the word rotation is used for angular acceleration because it was at rest. Now it starts rotating. When it rotates, its angular velocity changes from 0 to non-zero value. In which direction? It's very easy to say that the direction of alpha is, in this case, it is clockwise or in, either in or clockwise. Here the direction of alpha or the torque is outward or anti-clockwise. So, torque has a directional sense. It can be outward or it can be anti-clockwise. It can be inward or it can be clockwise. Well, now let us try to give the direction of the torque by the cross product of R and F. Either it will be R cross F or it can be F cross R. Let us see. When you are applying the force in this way, this is R vector, this is F vector. It is rotating in which sense? Clockwise sense. So this is the direction from R cross F, from R to F. Here force is in this direction, R is in this direction, R is in this direction, force is in this direction, and it is rotating in anti-clockwise manner from R cross F direction, R to F. The angle moves from R to F, and the sense of rotation of or sense of this angle gives us the direction of R cross F vector, that is outward in this case, and in this case this is inward. R to F, the sense of the angle is in, therefore the sense of R cross F is in, and the rotational effect of the torque is in, therefore the direction of the torque is given by R cross F vector. And the magnitude of R cross F vector can also give you the magnitude of the torque. Therefore, vectorially, the torque can be given as the cross or vector product of R and F. This gives us both magnitude and direction. This is one of the most important quantity in mechanics or entire physics. All along the life we have to use it as a turning effect of the force. Let me name it torque of the force about a point O. Torque of a force, which force? F, about a point O. Tau O, suffix is O. Tau O, torque about O. Torque of the force F, or turning effect of this force F, or twisting effect of the force F about this reference point.